All right. Hey, everybody. This is going to be the 1.5 intro video. So there's 1.5 intro notes, and then there's going to be 1.5 notes as well. For this video, we're going to be using the back of our periodic table a lot. So look at the periodic table that was at the front of your packet. Flip it over to the reference sheet. Okay. So just want to draw your attention to the metric prefixes. These are the prefixes that we put before units in the metric system. So if we start right here, like let's take grams as our base unit. So a kilogram is 10 to the third grams. A megagram is 10 to the sixth grams. A gigagram is 10 to the ninth grams, okay? Or meters. A kilometer is 10 to the third meters. A megameter is 10 to the sixth meters. A gigameter is 10 to the ninth meters, okay? This means 1,000. So a kilogram is 1,000 grams because 10 to the third is 1,000. A megagram is 10 to the 6 grams, which is a million grams. And a gigagram is 10 to the ninth grams, which is a billion grams. Okay? If you wanted to go up to 10 to the 12th, this is a prefix you probably heard before, is tera. Okay? So 10 to the 12th is a trillion. Okay? Like a teragram is a trillion grams, or 10 to the 12th grams. Tera is a capital T. You've probably heard these in terms of like computer stuff like kilobyte, megabyte, gigabyte, terabyte. So in any case, we don't use these very much in chemistry because we're mostly dealing with small things rather than large things. On the small side, a centigram is 10 to the negative 2 grams. A milligram is 10 to the negative 3 grams. A microgram is 10 to the negative 6 grams. A nanogram is 10 to the negative 9th grams. And a picogram is 10 to the negative 12th grams. 10 to the negative 2 is a hundredth. So a centigram is a hundredth of a gram. Milli is thousandth. Micro is millionth. Nano is billionth. And pico is trillionth. Okay? We deal a lot with these in chemistry. Okay? Like a nanometer, a billionth of a meter is a really good unit of measurement for dealing with atoms, the size of atoms, and for dealing with visible light waves. The wavelength of visible light that we deal with a lot in chemistry tends to be in the nanometers is a good unit for that. So be real familiar with the nano prefix. A nano whatever is 10 to the negative ninth whatevers, okay? Or a billionth of whatever, okay? In biology, you use micro a lot. A micrometer is a good length for measuring cells and things like that, but cells are a lot bigger than atoms. So nanometers are good for atoms, whereas micrometers or micrometers are good for cells. And that's why you use a microscope to see cells and things like that in biology, is because a microscope matches this. It's good for visualizing things that are, you could measure in micrometers. A microscope does not work for individual atoms. We would need a nanoscope, which we don't really have. Well, we kind of do. That's another story for another time. But okay, so these you will have on the AP exam to look at. I think the College Board just added this in the past few years, so it's nice you don't have to memorize what the metric prefixes mean. It's given to you here as well as the symbol that goes with them. And then down here, we're going to be using a lot of these formulas in our first unit about atomic structure. Okay, so these are the formulas that we're going to be using. Again, you'll have this formula sheet available on the AP exam, and this is what those formulas mean. Okay, so E stands for energy. The H stands for Planck's constant. Okay, it's always this number, so the H is always this number. It's joules seconds. Whenever you see two units right next to each other, they're being multiplied. So this is joules times seconds, okay? So H is always this number. Constant is the opposite of a variable. A constant is something that doesn't change, okay? So Planck's constant, H, is always this number. So you always plug that in for H. The energy is a variable. It can change, okay? The frequency is a variable. It can change. But Planck's constant is always the same number, okay? So when you multiply Planck's constant times the frequency of something, it'll give you the energy that thing has. I'll explain more about that later. I'm just kind of focusing on the formula. C stands for the speed of light, okay? The speed of light is a constant, okay? All electromagnetic waves, not just visible light, but all electromagnetic waves move at the same speed, okay? 2.998 times 10 to the 8th meters times seconds to the negative 1, or you could say meters times inverse seconds. Anything to the negative 1, means that it's in the denominator. Okay, so you could also think of this as meters over seconds or meters per second. Okay, so when you see something to the -1, it's per that. Okay, but it's hard to type meters per second on a computer, so a lot of times they'll just make this seconds to the -1 in the numerator rather than seconds to the 1 in the denominator. Okay, so the speed of light applies to all electromagnetic waves. They all move at the same speed. Okay, their wavelength and their frequency can vary. So these are variables, whereas this is a constant. So this is a Greek letter lambda. It stands for wavelength. I'll get more into what that means later. And this this V thing, it's actually a Greek letter that we call nu. It's not actually a V, but that stands for frequency. Okay, so the wavelength of a wave times its frequency always equals the same thing. Okay, so what we can infer from these formulas is that wavelength and frequency are inversely related. When one gets bigger, the other one gets smaller, because they always have to multiply to be the same number. They always have to multiply to equal the speed of light. So as the wavelength of a wave gets bigger, which means the waves get further apart, the frequency gets smaller. Okay, the waves become less frequent when they're further apart, which makes sense. Okay, as the wavelength gets smaller and the waves get closer together, the frequency gets higher. Okay, so as this number, this wavelength gets shorter, the frequency gets higher. The frequency is literally how frequent the waves are. So these, we can tell from the formula, must be inversely related. When one of these gets bigger, the other one must get smaller, because they always multiply to be the same thing. Up here, H is the constant, okay, whereas E and nu, the frequency, the energy and the frequency, the nu stands for frequency, must be directly related, right? Because they're on opposite sides of the equal sign. So H is always the same thing. So as frequency gets higher, energy must be getting higher, right? H is always the same thing. As frequency gets lower, the energy is going to get lower, okay, based on this equation. And I'll show you what I mean by looking at actual waves in a second. So just keep in mind, you'll always have this to look at, okay? All right, so spectroscopy, that we're going to be focusing on a lot. Spectroscopy is when you shine light on a chemical sample, and what's given off by the sample gives you some information. A lot of the light that we use in chemistry is within the visible range, okay? So I'm going to show you something that is not in your packet, but that will help tie what I'm saying back into maybe what you've learned in the past. Okay, this is not in your packet. This is just from the kind of filling in some background information. So you may have in the past, or maybe not, which is okay, learned about the electromagnetic spectrum, okay, which is electromagnetic waves are very unique. They're energy waves that can travel through nothing. So they can travel through outer space. They don't need a medium to travel through. Sound waves need something to travel through. They need to travel through a gas like air or a liquid, or something has to carry a sound wave. Electromagnetic waves can travel through empty space. So these are bouncing around all over outer space. They can also travel through gases and sometimes solids and liquids, depending on the nature of the solid or liquid. So these can travel through air, they can travel through our atmosphere, but they can also travel through nothing. The sun, the center of our solar system, emits mostly 43% visible light, and the rest is mostly infrared light or ultraviolet light. Okay, so we can't see infrared or ultraviolet, but we can see visible light. So the sun mostly emits in this range, okay? So that's why the sun was here before humans were here, okay? So that's why life on Earth evolved to detect sunlight. Plants on Earth, visible light. Life on Earth evolved to detect visible light. That's why our eyes can see this light, okay? This is visible to humans because it's a large part of what the sun emits. So this is a big type of light that exists on Earth, so we evolved to see it, okay? It helped us survive and navigate life on Earth. Plants evolved to use this type of light in photosynthesis, okay? So the sun was here first. It emits these, okay? The biggest chunk of which is this, so a lot of life on Earth kind of evolved around this, okay? But visible light's only a very narrow part of the spectrum, okay? It incorporates red, orange, yellow, green, blue, indigo, and violet light, okay? The rest of the spectrum humans cannot see. It's the same type of wave, just with a different frequency and wavelength, but can travel through nothing. They all move at the same speed. They all move at the speed of light, okay? It's just the differences in the wavelength and the frequency leads to differences in energy. So we can't see these or these, but they're the same type of wave, okay? It just so happens that visible light has the exact amount of energy that electrons release and absorb, okay? Valence electrons release and absorb in the visible range. So we tend to use visible light a lot in spectroscopy because it can be absorbed by valence electrons and then emitted by valence electrons. Valence electrons are electrons in the outermost energy level. If you wanted to get energy to the inner core electrons, you would need more like X-rays. You would need higher energy waves. So these can be absorbed by the inner core electrons. If you wanted to excite like an entire molecule, if you wanted to make a whole molecule start spinning or moving faster, that would be more like the microwave range, okay? So matter can absorb and release all types of energy, but visible light, it can be absorbed and released by valence electrons. So that's why we're going to focus on visible light range in our lesson today, okay? So spectroscopy is when energy is added to atoms and molecules, light's absorbed and released, and it can tell us important information about the molecule. Since we can't see atoms and molecules, a lot of times we have to shine light on them, see what's absorbed, see what's released, and make inferences from there, okay? Electromagnetic waves are very poorly understood. They don't follow Newton's laws of motion. They have their own set of physics. Newton's laws of motion physics doesn't apply. They have their own set of physical rules called quantum physics. Quantum rules only apply to things that are really, 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 really small, like particles of light, particles of electromagnetic radiation. So one facet of quantum physics is that particles have wave-like behavior and waves have particle-like behavior. And by that I don't mean that the particles are moving in a wave. It means they have this kind of like repeating, kind of cyclical nature to their properties. It's very hard to understand from our Newtonian perspective, okay? We're in the perspective of Newtonian physics. If I throw a baseball, it's a moving particle. If I go to the ocean, I see waves. They're two different things. But for things that are very, very small, like electrons or electromagnetic waves, particles behave like waves and waves behave like particles. So we can think of electromagnetic radiation as being waves. We can also think of it as being particles. And when we think of it as particles, we call it photons. So a photon is a particle of electromagnetic radiation. A lot of people say a particle of light. When people say light in science, they often mean any type of electromagnetic radiation. They call all of these light. A small part of that is visible light. And the visible light is mostly what we're going to focus on in this lesson. So when I say photons, I'm talking about a particle of light that can hit a valence electron and be absorbed by that valence electron and then emitted by that valence electron when it kind of falls back down to its normal energy state. Okay, so some important relationships about photons, okay? The energy of the photon is equal to Planck's constant times the frequency, okay? And like we said, this is on your formula sheet. This is Planck's constant. So that means when the frequency goes up, the energy goes up, okay? So higher frequency waves mean higher energy, okay? And higher frequency is like this. The waves are more frequent. So these are higher frequency, higher energy. These are lower frequency, lower energy, okay? And then this formula, it's been flipped from what's on your formula sheet. You might want to change it. What it shows on your AP formula sheet is C equals lambda times nu, okay? It's not a V, it's like a V blowing in the wind, okay? So don't say V, you say nu. It's a Greek letter that looks like a V blowing in the wind. This is on your formula sheet. This is the wavelength, and this is the speed of light, 2.998 times 10 to the negative 8th meters per second. So the speed of light is constant. It's always the same, okay? All electromagnetic radiation moves at the speed of light, what we call the speed of light. It's these that can change, okay? So as wavelength gets smaller, frequency gets bigger. As wavelength gets bigger, frequency gets lower, okay? These are inversely related. So here's what I mean by that. If you look at your electromagnetic spectrum, the wavelength is the distance between waves, okay? So on this end, we have longer wavelength, lower frequency, okay? So longer wavelength or bigger wavelength means a smaller frequency. The waves are less frequent. And lower frequency means lower energy. These are low energy waves. They're very safe, okay? Where on this end, these are shorter wavelength, a smaller wavelength, but a higher frequency, okay? And higher frequency, like we said, means higher energy. So X-rays can get into your body. We use them to image our bones, but they're also kind of dangerous. That's why when you get an X-ray, the technician goes out of the room to turn on the X-ray because they don't want to get bombarded by X-rays all day, every day. That's why the parts of your body that aren't being X-rayed are covered by lead, because X-ray, that's the one thing an X-ray can't get through is lead, and they want to minimize your X-ray exposure. When you have to get an X-ray, they only want it to hit the parts of your body that they have to. You also can't get an X-ray when you're pregnant. That's why they don't use an X-ray to image babies. They use an ultrasound, which is sound waves, which is not an electromagnetic wave. So X-rays are kind of dangerous. Gamma rays are the most dangerous. These are very high energy. They can get into anything and cause cancer. There's a big issue with like nuclear weapons. When nuclear weapons were used in World War II by the US on Japan, gamma rays got into people's bodies and killed their organs while they were still alive. So these are very, very dangerous, high energy waves, whereas these are much safer, okay? Okay. The thing is, in upper level science, the spectrum is often flipped the other way. Okay, a lot of times in lower level science, you'll see the spectrum this way, going from low energy to high energy. So going from radio to microwave to infrared, and then into the visible red, orange, yellow, green, blue, indigo, violet, ultraviolet, X-ray, gamma ray. Quite often in upper level science, it's flipped the other way, where we start with high energy, gamma, and end with low energy. And you'll see Roy G. Biv, the visible spectrum, flipped to VIBGYOR, okay? So get used to that, because we're in upper level science now. So get used to seeing it in this way, where this is the wavelength, okay? When you see meters, this is nanometers, but when you see a length, they're talking about wavelength, okay? So you can see the wavelength is getting bigger and bigger and bigger, okay? Whereas in this way, the wavelength got smaller. They flipped it. Here, the wavelength is getting bigger. So the biggest wavelength is the red, and then go red, orange, yellow, green, blue, indigo, violet, like that. So get used to seeing it VIBGYOR rather than Roy G. Biv, okay? And that means on this end, we have the short wavelength, high frequency, and on this end we have the large wavelength, low frequency, okay? So within the visible spectrum, the red light is lower energy and the violet light is higher energy, okay? Equations 1 and 2 can be combined. So equation 1, E equals Planck's constant times nu. Energy is Planck's constant times frequency. More frequency means more energy. Okay, just like we said, this is more frequent, more energy, right? Less frequent, less energy. And what we're going to do is take our second equation and rearrange it. Okay, so we're going to rearrange it so that nu is on one side by itself. So I'm going to divide both sides by lambda. And when I rearrange that, I have C over lambda equals, lambdas cancel out here, equals nu, okay? And what that means is that I can plug this in for nu here, and I'll get a new formula, E equals H times C over lambda, okay? So again, that's nothing fancy. All I did was plug one equation kind of into the other, all right? So energy equals Planck's constant times frequency. If you don't know the frequency, though, but you do know the wavelength, you can just use this formula instead, okay? It just depends on what they give you. In our practice problems today, we're, I think, only going to be using these formulas separately, but you can kind of combine them if you need to. And then sometimes you need the energy of a mole of photons, and that means you would just multiply it by Avogadro's number, okay? So if you wanted to know the energy of one photon, one particle of light, okay, you could use this formula. Like that, okay. And if you do that, the answer will be in joules, okay? The answer will be in joules. And you'll see when we do problems, you'll see how all the units of measurement kind of cancel out and you end up with just joules. If you needed to know a mole of photons, the energy of a mole of photons, all you would do was multiply this, do energy equals hc over n, and you would multiply it by Avogadro's number. Na is Avogadro's number, okay? Which, if you forget, it's on your reference sheet. Where is it? Oh, right there. There you go. Avogadro's number. Na is Avogadro's number. It's right there. Okay. And the answer would be in joules per mole. Okay. Because you can see Avogadro's number, the unit is moles to the -1, which means per mole. Just like seconds to the -1 means per second, moles to the -1 just means per mole. Okay. So you're taking the joules and you're multiplying it essentially by something with per mole in it. Okay. All right. So what we have here is a couple. I'm just going to cover up this answer. I don't really like the way that they did it. Okay. So I'm just going to, you don't have to write this down because the answer's already been written down. Just kind of listen to my explanation. So calculate the energy in joules of a photon of red light having a frequency of 4.00 times 10 to the 14th hertz. Okay. So we know the frequency and it's asking for the energy. So we're going to use this formula, okay, E equals h nu. Okay, so we know that h, Planck's constant, is 6.626 times 10 to the -34th joules seconds. Whenever you see two units next to each other, they're being multiplied. So it's joules seconds or joules times seconds, okay? So that's what we plug in for h. This is frequency, okay? 4.00 times 10 to the 14th. Hertz is the same as per second, okay? I wonder if it said that on the front. So frequency is in hertz or per, hertz means per second, okay? So I'm gonna switch to seconds to the -1, okay? And then all you do to calculate the energy in joules is you multiply these by each other, okay? So do 6.626 times 10 to the -34th times 4 times 10 to the 14th. All right, and you get 2.65 times 10 to the -19th. And now let's look at our units, okay? We have joules times seconds times seconds to the -1. Okay, so seconds to the first times seconds to the -1st. Whenever you're multiplying things that have the same base, you add the exponents, okay? 1 plus -1 is 0. Anything to the 0 power is 1, okay? So it's just joules times 1, which means it's just joules, okay? So energy is 2.65 times 10 to the -19 joules. And that makes sense because joules is a unit of energy. Another way you could think of this is joules times seconds and then divided by seconds. So when seconds is in the numerator and the denominator, it obviously cancels and we're left with joules. So however you want to think of it, that's how we got the answer, okay? And that matches what they have up here. And it's joule. The reason they wrote joules per photon is because it's for one photon, okay? This thingy right here was just a conversion factor for getting out of hertz and into seconds to the -1. I just simply replaced it. So when two units are the same, you could either write hertz or seconds to the -1. I just replaced it. Or if you want to be real official, you can make this little conversion factor. 1 second to the -1 is the same as hertz. So hertz here is in the numerator, so it'll cancel. and we're left with seconds to the negative 1, and then seconds times seconds to the negative 1. It all went away. So that's why we were just left with joules. Okay? All right, second one, I'm going to do the same thing. I'm going to cover this up. Convert this frequency into wavelength in nanometers. Okay? So we have our frequency from the original problem, 4.00 times 10 to the 14th hertz. I'm just going to write seconds to the negative 1. Okay. We want to convert this into wavelength. So for this one, we're going to use the other formula. C equals lambda times nu. Okay. So this is our wavelength. Okay. And C, if you look at your formula sheet, it's always the same thing. 2.998 times 10 to the 8th. Meters times seconds to the negative 1. I'm going to write that as meters per second. Equals lambda times 4 times 10 to the 14th per second. Okay, seconds to the negative 1 is like having seconds in the denominator. Okay, so I got to get lambda by itself. Lambda is being multiplied by 4 times 10 to the 14th, so I'm going to divide by 4 times 10 to the 14th per second. Divide by 4 times 10 to the 14th per second. Okay, so on this side, lambda times this divided by the same number, that cancels. We're left with lambda. And then 2.998 times 10 to the 8th. So type that in, divided by, be sure you put the denominator in parentheses, 4 times 10 to the 14th. And you get 7.49. Let me be sure that's right. Yeah. 7.495 times 10 to the negative 7th. Okay, so I'm just going to round that to 7.50. Remember, E means times 10 to the. Okay, 7.50 times 10 to the negative 7th meters. So we had meters per second divided by per seconds. So the numerator had seconds to the negative 1. The denominator also had seconds to the negative 1. So that just kind of goes away. And it makes sense. Wavelength is a length, so it makes sense that it's in meters. Okay. Notice though that the question was asking for the nanometers. Okay. This equation gave us in meters because the speed of light was in meters per second, so our answer is in meters. Now we need to convert that to nanometers. So the best way to do that is dimensional analysis. 7.50 times 10 to the negative 7th meters. Throw meters under the bus, and we want to get to nanometers. Okay, so look at your formula sheet. 10 to the negative 9th meters is what a nanometer is. Okay, nanometers are very, 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 very small. Okay, it's 10 to the negative 9th meters, or 0.000000001 meters. Okay, so it's 10 to the negative 9th. Whoops. 10 to the negative 9th meters is 1 nanometer. Okay, so cancel meters, and then just type that in your calculator. 7.50 times 10 to the negative 7th times 1. I'm not going to type that in. Divided by 10 to the negative 9th. Okay, and you get 750. Okay, and just double check that that answer makes sense. Okay, it said this is a photon of red light. It's a particle of red light. So let's just be sure that this is in the red range. So look at your chart right here at these are the wavelengths. Okay, so 750 would be like right after this right here. Okay, so it would be within the red range, more or less. Might be almost out of the visible range, but again, we're like in the right ballpark if that's 700, so that our answer makes sense somewhat. Okay, and for part C, what is the energy of 1 mole of these photons? Again, I'm just going to do it my own way. So the energy of 1 photon from part A is 2.65 times 10 to the negative 19th joules. That was the energy of 1 photon. So a mole of photons, we would just multiply it by Avogadro's number. Okay, 6.022 times 10 to the 23rd. It's right here. And remember, that's moles to the that's the number of things per mole, or moles to the negative 1. Okay. So I'm just going to multiply those together. 2.65 times 10 to the negative 19th times 6.022 times 10 to the 23rd. Okay, and that's our answer. Let me be sure it matches. Yeah. So 159,583 joules times moles to the -1, or you could say joules per mole. Okay. And that makes sense, okay? There's this many particles in a mole, okay? So if this is the energy of one photon, it makes sense that we would multiply that by the number of things in a mole to get the energy of a mole of photons, okay? Which is a much, much bigger number. This is a much bigger number than, this was a tiny number. This is a much bigger number of joules. This we could never detect in the lab, the energy of one photon. I mean, that's just such a small amount of energy. But once you group things into moles, it's enough energy that we can actually like notice it, okay? So we scale it up to a mole of photons. That's a reasonable number, okay? They wrote it in scientific notation, which is fine. If you want to convert this to scientific notation, this is where the decimal is now. Just move it till you get a number between 1 and 10, okay? Don't stop here. 15.9 is not between 1 and 10. 1.59 times 10 to the 1, 2, 3, 4 times 10 to the 5th joules per mole. And if we want to round that off, we can round it to 1.60, okay? Times 10 to the 5th joules per mole. Okay, that's where they got that from. All right, so a couple more practice problems. What is the frequency in hertz of light having a wavelength of 4.63 nanometers, and what is the color of this light? So pause the video and try to do it on your own first. You find the formula on here that you want to use, and then unpause the video and I'll explain it. Okay. So what is the frequency in hertz? We're given the wavelength. We want to know the frequency. Okay, so the formula that has wavelength and frequency is this one, C equals lambda times nu. Okay, the problem is C, the speed of light, is in meters per second, or meters times seconds to the -1. So we've got to get this to meters before we plug it in. We can't plug it in nanometers because then the units won't cancel correctly. So we're going to do a little side conversion, 436 nanometers. Do some dimensional analysis. I wrote that kind of weird. Throw nanometers under the bus. We want to get to meters, okay? So a nanometer is very small. If you look back at your formula sheet, a nanometer is a billionth of a meter, or 10 to the -9th meters, okay? 10 to the -9th meters is 1 nanometer, okay? So cancel nanometers, type in 436 times 10 to the -9th. You get 4.36 times 10 to the -7th meters. So we're going to use that. Always plug it in meters because C is in meters per second. So the wavelength, lambda, 4.36 times 10 to the -7th times frequency. So to solve for frequency, we're going to divide both. We got to isolate the variable. So divide by 4.36 times 10 to the -7th. Divide by 4.36 times 10 to the -7th. Bring down your equal sign. So this side simplifies to nu, or frequency. This side, oh, I'm going to put meters after that. Okay. 4.36 times 10 to the -7th meters. So we're going to simplify the other side. 2.998 times 10 to the 8th divided by, open parentheses, 4.36 times 10 to the -7th. All right, and you get I'm going to round that to 6.88. Don't forget this part, times 10 to the 14th. Okay, 6.88 times 10 to the 14th. Okay, and we have meters times seconds to the -1 divided by meters. So meters cancels, so our units are seconds to the -1, or per second. And that makes sense because that is a unit of frequency. So it means that many waves per second. That's how many waves are passing a given point per second. So the frequency of electromagnetic waves is quite high within the visible range, which is mostly what we're dealing with here. Okay, next one. Let me just check my answer. Can't be sure that's right. Okay, another way you could say it you could also say 6.88 times 10 to the 14th hertz. Okay, hertz and seconds to the -1 are the same thing. Okay. Number 2, sodium vapor lamps are often used in residential street lamps. These are kind of being phased out. A lot of street lamps now are not yellow light, they're very white light because they're switching to LED lights. But back in the day, or if you still see older street lights, especially on interstates, like on the highway, a lot of times they have a yellow tinge. Those are sodium vapor. Sodium is a metal. It's not, salt is sodium chloride, but sodium by itself is a metal, but it can be vaporized into a gas. And when you run electricity through it, it emits very bright in the yellow range. So it made a good bulb color for street lamps. So that yellow light has a frequency, it emits a very specific yellow color. Yellow is like a range of frequencies, but it emits this specific frequency. Okay, so what is the wavelength of this light? So we're going to use our formula that has frequency and wavelength. C equals lambda times nu. Okay. So once again, C is the speed of light, 2.998 times 10 to the 8th, not -8th, meters times seconds to the -1. Lambda this time is our unknown. Okay, so I'm just going to write lambda. And then frequency, I'm going to write 5.09 times 10 to the 14th. And instead of writing hertz, I'm going to write seconds to the -1. Okay, so to get lambda by itself, you just divide by 5.09 times 10 to the 14th seconds to the -1. Okay, so on this side, we're left with lambda by itself, and type this in your calculator, 2.998 times 10 to the 8th divided by, open parentheses, 5.09 times 10 to the 14th. Close your parentheses. And you get 5.89. We're going to round that to 5.89 times 10 to the -7th. Is that right? 5.89 times 10 to the -7th meters. Yeah, that's right. Okay. And it's asking for it in nanometers. Again, the speed of light is meters per second, so it'll always give us wavelength in meters. We need to convert that to nanometers. So take 5.89 times 10 to the -7th meters. Throw meters under the bus. We want to get to nanometers. And again, check your formula sheet. A nanometer is 10 to the -9th meters. Okay, it's a very small amount of meters. So 1 nanometer is 10 to the -9th meters, or a billionth of a meter. Cancel meters. Okay, multiply straight across the top, you get 5.89 times 10 to the -7th. Multiply straight across the bottom, you get 10 to the -9th, and then you do top divided by bottom. Okay, so I'm just going to use the answer that was already in my calculator. Press divided by, that takes that answer and reuses it, 10 to the -9th. And you get 500, and I'll round that to 589 nanometers. Okay, and let's just double check that makes sense. Okay, this is yellow light, so let's flip back to the previous page and be sure that this wavelength is within the yellow range. So the yellow range right here is 600, so 589 would be right about here. So that would fall within the yellow range. Remember, this is a continuous spectrum. It's not just 600 that's yellow. It's like anything from here to here is in the yellow range, okay? And the color emitted by sodium is specifically just this specific color, the 589 nanometer version of yellow, okay? So I know a lot of this looks complicated just because of all the symbols. A lot of these Greek letters make things look very difficult and high level. Numbers in scientific notation make things look really difficult, but the actual algebra that you're doing is extremely simple. Just basic algebra, you know, plugging in for two things you know, solving for the one thing you don't, with these very simple equations. So hopefully, even though it looked intimidating at the beginning, you realize this stuff really isn't too bad, especially because it's all right there on your formula sheet, including all the constants, so you don't really have to memorize anything. Okay, so that's it for 1.5 intro. The next video will be the actual 1.5 lesson.